Okay.
Shall we start?
Okay, may I introduce Thomas Loredo from Cornell, one of the country's most distinguished astrostatisticians, experienced, and he will talk about a Bayesian look at periodograms for us with an astronomical tilt. Okay, Tom, the floor is yours.
Thanks, Eric. Yes, we'll talk about periodograms from largely from a Bayesian perspective, but not entirely, and indeed from an astronomical tilt, which they had since their very origin. So let's start by talking a little bit about the motivation and the historical origin. As you know, if you're attending this course, there's a lot of variability in the cosmos. Things move, things vary in position, things vary in brightness. And we need go no further than our own closest star, the sun, to see some of this variability. Some of the earliest variability quantitatively studied in the sun is the number of sunspots as a function of time, and that's this red curve here as a function of year. The sun was first examined telescopically around 1610, and that's when people started to count sunspots in a systematic way. Sunspots had been observed back to millennia, but with the naked eye, as you can imagine, it's hard to look at the sun and resolve spots. So around 1610 is when the quantitative study began, and you could see there's this cyclical behavior. I wouldn't call it periodic, but there's some kind of evidence of periodicity. Certainly if you were just to look at the times of the maxima, the local maxima, it would probably look very periodic. The separation is about 11 years. So that's called the solar cycle, the 11-year solar cycle. Modern observations have revealed that the magnetic fields coming out of sunspots actually flip sign every other cycle. So in fact, it's believed that the underlying physical mechanism is a 22-year cycle. If you take into account the sign of the magnetic field, things only repeat every 22 years, not every 11 years. But from the point of view of looking at the surface of the sun, there's this 11-year cycle, but there's other variability going on. This black curve is it's like a 15-year smoothing. And so the red curve shows this oscillatory behavior. These other curves show some more kind of gentle, you might call it secular variability. On the right plot here is just, let's see, a year and a half of higher frequency measurements of the solar irradiance, the total amount of light energy that we get from the sun. It's measured in watts per square meter, so there's about 1,300 watts per square meter that we get on the surface of the Earth from the sun. These are images of the sun. This is a broadband look at the sun in red light, and then this is a measurement of the strength of a certain calcium line and a strength of the magnetic field. And so you could see a large sunspot group here and here, a smaller one over here. Actually, it's the same one, I think, rotating around. And what you see here is the total solar irradiance, and you can see these two correspond to times near this minimum, the point being that this large sunspot group is causing the sun's total light to dip by about 0.1%, a part in 1,000. So the point of this is just that sunspots, we believe, can tell us something about the solar irradiance. Actually, this is somewhat misleading. In fact, when there are lots of sunspots, besides the obvious dark spots on the sun, the solar disk actually has a lot of this kind of network of structure that actually brightens when there are a lot of sunspots. And they more than make up, most of the time, they more than make up for the dimming of the sunspots. And in fact, at the peaks of the sunspot numbers, the sun is actually very slightly brighter than it is at other times. But the point of this is just that the sunspots do tell us something about the solar irradiance. You could see there is not so much of an effect in the ultraviolet. So in fact, the color of the sun is changing. The spots are affecting the red more than they're affecting the ultraviolet, which is what this plot shows. So that's just to say that there can be variability that's complicated, not just in the total amount of electromagnetic energy from an object, but in its color. The other thing is that this variability looks very stochastic on these, sub-year timescales. These are like months and weeks. So you're seeing several types of variability here: this oscillatory, this long time secular behavior, and this short time scale stochastic behavior. In addition, yes.
Just to say about the history, there are endless reports of other cycles, particularly a 1 in 56 day cycle, and widely respected. And they keep on making periodograms, and they keep on finding peaks, and they keep on reporting them. There's an enormous literature. Most of it, in my opinion, is somewhat dubious, but some of it is not. Excuse me.
No problem. So besides those types of phenomena, there are also transient phenomena happening on the sun's surface: solar flares, coronal mass ejections, these large ejections of matter, which we can actually see the radiation from them. And these show that, so remember the irradiance of the sun was of order 1,300 watts per square meter, so you can see these are quite small compared to the total irradiance of the sun, but nevertheless they're bright. But these are very localized transient events that happen unpredictably, somewhat randomly in time, with very different scales in terms of their amplitude. So you see all these different types of variability, which you've talked about in the course: oscillatory, secular, stochastic, transient. And so we can see all those things just in the sun nearby. And of course, when we look at the diversity of stars and other objects in the universe, we see many other types of behavior. Here's another. This is going over times even longer than the few centuries we were looking at earlier. So the blue curve here is what was in red before. That's the sunspot numbers. And then I mentioned that correlated with solar activity are these coronal mass ejections, these large emissions of bubbles of gas from the sun. There are more of them near the peaks. And some of the matter that's released in these mass ejections reaches the Earth, gets incorporated into the atmosphere and the soil at the Earth. And so we can measure unusual isotopes that are produced by the sun, in this case beryllium-10 and carbon-14. We can measure them in tree rings and in ice cores, and we can see that over the time of the historical record of sunspot number, that they trace the kind of that kind of 15-year smoothing that we were talking about before. It's much lower where there's low secular trends in activity and much higher here. So that's the empirical argument why you might consider those tracers to be good historical markers of the sun's irradiance as a function of time. So that's some of the work that goes into studying the possible effect of the sun on the climate. Okay, so again, just very long time secular activity. So trying to quantitatively study these phenomena on the sun and the potential relationship of those phenomena to phenomena on the Earth, like meteorological phenomenon, led these folks to introduce the techniques that we now understand are called periodogram techniques. So they both were physicists that started their careers at the Cavendish Lab. If you're a physicist, you probably know that name. That's where Maxwell worked, Maxwell's equations. So Lord Rayleigh was the professor who succeeded Maxwell. He had the same professorship, the Cavendish professorship, in fact. So he spent a lot of his career at Cavendish Lab and then moved to the Royal Institute of Great Britain. He's very famous for study of physical oscillatory phenomena, different types of waves. He's the discoverer of Rayleigh scattering, the phenomenon that makes the sky blue. It has to do with the wavelength dependence of the scattering of sunlight off of dust in the atmosphere. He's one of these fellas who have an actual unit named after them. The Rayleigh is a unit of acoustic impedance. He wrote a very influential book on the physics of sound, vibrations in the air, and that's where the Rayleigh unit originates with his studies of sound. Schuster began working at Cavendish Lab under Maxwell and then worked under Raleigh, and we'll see that that's an important connection in a moment. And then he moved to Owens College, where he founded a lab that competed with Cavendish Lab. And he was succeeded by the physicist Rutherford there. So I think Schuster's name is not so well known to physicists, maybe more so to statisticians. But he was a very famous physicist at the time. Actually, when he moved to Owens College, his professorship was in applied math, even though he started in physics. So they're going to be the main players in this story. And so Schuster was the first one to really worry about trying to quantify evidence for detecting periodic signals in time series such as we just saw. Now, the 11-year cycle of the sunspots was very obvious. He referred to that as an obvious periodicity. But what was happening at the time is people had just discovered that the sun was rotating by studying the study of sunspots, about 26-day period, and people were trying to see if there was evidence of that rotational period in the number of sunspots, in weather on the Earth. People were looking for periodicities in the occurrence of earthquakes around the same time, using some of the same kind of ad hoc techniques they used to study the periodicity of sunspots. And so Schuster worried about hidden periodicities that you couldn't be sure were real because different effects in the data could be misleading you. No one has so far discussed the very essential question whether the results obtained may not be due to merely accidental circumstances. So that was his concern in this famous paper from 1898. So it's the object of this paper to introduce a little more scientific precision, in particular, the theory of probability. So we want to assign a definite number for the probability that the effects are real and not due to accident. So that's what he set out to do in this paper. He invented in this paper something that's called the Schuster periodogram, but he actually invented two different periodograms, and the main part of our class today is going to be split into two parts on those two periodograms. In the first part of the paper, he describes a periodogram, and then he says there's this other class of periodicity. He means a periodicity in magnitude of a quantity. The case he treated earlier was the periodicity of occurrence of quantities. So what he's distinguishing here are arrival times of events. So it could be, cars passing you on the street. In this case, it would be if you were looking at the sunspots not in number, but maybe looking at the times of the peaks. So times of events. In my case, I've worked a lot on arrival time series. It's times of arrivals of photons in a telescope seen from some distant astronomical object. So those are the first thing he discussed, so the occurrence periodogram, and then he was also interested in magnitude. So if you were to actually look at the time series of sunspot number, but look at it as a function that takes on some magnitude as a function of time, and you want to know, is there a pattern in how the magnitude grows and shrinks, that's periodic. So those were the two types of periodograms that he talked about, and this in a nutshell I just actually snipped from his paper, the way he thought about this. So this first one that he came up with, which he referred to as a occurrence type of problem, what he invented was what we now call the Raleigh statistic. And this was the kind of construction he had. So suppose you have some candidate period. Think of having a timeline where you draw the events on it. And then suppose your timeline is 10 days long, and you're considering a possible period of 1 day. So wrap the timeline around a circle whose circumference is 1 day. So this is the timeline, but folded, wrapped around. And then draw a unit vector from the origin of the circle to each event that you see. And the intuition is that if things are periodic on that time scale, then those arrows will cluster in some special direction corresponding to the reoccurrence at that period. Like there's some evidence of clustering the way I drew this. But if there isn't if there isn't actual periodicity at that candidate period, then they should lie uniformly randomly on the circle. And so he just said, well, let's just add up the lengths of these vectors. Think of these as vectors. Start with this one maybe, then take this one, translate it so that its tail is on its head, then take this one and add it. And he asks, what's the magnitude of that resultant vector? So you just take the components projected along the x-axis, so the cosines, and then square them. Take the components along the y-axis and square them, and then take the square root of those. So it's the magnitude of the resultant vector. This defines this quantity R, which is the statistic, which we now call the Rayleigh statistic. In the case where you're actually measuring something that's a magnitude that you're sampling at some chosen times, the magnitudes are what he's calling capital T here. Now these vectors each have a length, the T1, the T2. The theta 1 and the theta 2 mark the times on the circle. And so you just do the same trick, but now you're adding vectors that have a length. And again, you expect them to sum to something near 0, but not exactly if it's just random. But you expect them to kind of tend to go in one direction. You don't know which one a priori, but to some direction if there's actually a periodic signal. And then to do some kind of probability calculation with this, you need to make some hypothesis about the actual distribution and calculate the probability distribution for these sums. And to do that, that's where Rayleigh comes in. So Rayleigh was working on a problem in sound where there were lots of sinusoidal vibrations from random sources, uncorrelated in phase, and he asked what's the probability distribution of those. And so Schuster recognized that this is that same problem. The sines and the cosines here were just the phases of the waves that Rayleigh did. And this distribution is now called the Rayleigh distribution. And so he recognized that this is the null distribution for this, and he wrote down how to calculate p-values from that null distribution. So that's Schuster's calculation in a nutshell. So this is the Rayleigh statistic. This is what's called the Schuster periodogram.
So there was no reference to Fourier.
Yes, so he wrote these down, and then later in the paper he just starts using the term Fourier series. He didn't use it until he actually wrote the formula down, but my reading of the paper is that Fourier was so much well understood at the time that he didn't have to say this was a Fourier series. Later on in the paper, when he refers to properties of it, he said, we can calculate this Fourier component this way or whatever. People would have just recognized it. So, all right, so where does this term periodogram come from? So it comes from Schuster being a physicist. He makes an analogy. He actually wrote an entire paper. This is from his first paper, but he wrote a separate paper on what he called the optical analogy to hunting for periods. He makes an analogy. He thinks of the periodogram as kind of a prism, where just as a prism separates light into and spreads it out spatially according to the frequency of the light, he thinks of the periodogram as doing something like a spectrum, but for periodicity in time of some time series. So it's convenient to have a word for some representation of a variable quantity which corresponds to the spectrum of luminous radiation. So instead of spectrogram, he called it the periodogram. And then he pointed out that when you hear notes, that would correspond to having a spectral line, so you expect a very narrow feature. But he also pointed out that a noise would be a periodogram showing a broad band. So he had in mind the possibility that the periodogram could tell you about other features besides pure periodicity, though that was the focus of his work. So periodograms were invented to discover and measure periodic variability. They are also useful for characterizing stochastic variability. I might have one slide, which I didn't write, but I'll write on the board where I'll say something about that. But the focus of the talk today is on, this should be periodic signal detection and characterization. How do you detect whether a periodic signal is present or not, and then if it is, how can you measure its properties? Measure its period, measure the shape of the waveform that's repeating. Okay, so if you recall that sunspot number chart, it looked oscillatory, but certainly not purely periodic. But in astrophysics, there are phenomena that are extremely close to being truly periodic. So these strongly motivate thinking about things like periodograms and thinking about trying to identify signals that really are periodic, not just approximately periodic, but as far as the data could tell, strictly periodic. So this is an example that drove my early interest in this topic, which was studying pulsars. So these are the dead cores of massive stars. A star several times the mass of the sun. Its core would be about the mass of the sun, but at the end of its life it collapses to about the size of Durham. It's an entire solar mass in about 10 kilometers. And these objects, just like a skater closing her arms and spinning up, the sun, which our sun rotates about every 26 to 38 days, depending where you look on the sun. Once you take that angular momentum and shrink it down to 10 kilometers, the resulting object can spin as fast as 1,000 times a second. That's the fastest ones we see. The typical ones are a few tenths of a second to tens of seconds, their periods. And they emit all different types of radiation, so we see them in radio waves and in optical light, and for the data in those cases fall under the magnitude type of periodogram that Schuster talked about. So in radio, we measure at regularly spaced times, we measure how much radio power is reaching the telescope. Sometimes it's converted into an actual temperature in the telescope. So this is some amplitude as a function of time. Similarly with optical light, at different times we'll measure the flux that's entered the telescope. Sometimes we'll count photons, but usually it's just reported as integrated flux. But in the area where I began my career, high energy astrophysics, we look at X-rays and gamma rays, very energetic forms of radiation, much more energetic per photon than radio or optical, but much rarer, much less in number in terms of photons reaching the Earth. So we actually detect and count individual photons. And so the best data that we have on X-rays and gamma rays from pulsars are actually arrival times at the Earth of individual photons. And so what's shown here is just binning in time so that you can have something that's easy to interpret, to plot, a binned kind of time series, but in fact the actual data are arrival times of events. So these types of data are what Schuster was talking about, occurrence of events, as opposed to a magnitude measured at a chosen time. One caveat I want to say about pulsars is they're not strictly periodic. The period is a linear function of time. Sometimes there's a quadratic term. The pulsars are, as they emit energy, they're actually losing some of their spin. The spin energy is being converted into radiation. As a result, they spin down incredibly slowly. It takes hundreds of thousands of years for them to spin down appreciably. Well, thousands of years when they're born, but as they get older, then it's tens of thousands of years. So over the time frame of any particular single observation, their period is essentially constant. So that's one type of periodic phenomenon in astronomy. Another that you've heard about, I'm sure a lot here, is our exoplanets. And here are measurements of the line of sight velocity to a star that we now know is hosting an exoplanet as a function of time with errors. And this is not an obviously periodic signal. So in this case, what's hiding the periodicity is the kind of strange cadence of the measurements. They're very irregularly spaced in time. If you fold them with the right candidate period, this is what those same data look like as a function of phase of the period. The period is 62 days or two months over these 15 years or so. And then we'll talk more about periodograms in a minute, but this is what the periodogram looks like. It's a function that has a peak at the best period where you can fold and find something that actually does look periodic when it's appropriately folded. So that's the looking at the reflex motion of a star as a planet revolves around it. You know, the star is pulling the planet, but the planet is pulling the star with the same force. Of course, that same force has much less of an effect on a massive star than it does on a planet. So the star is only moving a little bit, on the order of meters per second, running speed, but we can measure that spectroscopically with Doppler shifts. We also see exoplanets, as you've talked about transits, I assume here, where by fortuitous alignment, if a planet's orbit makes it pass between the star and us, the star will get somewhat dimmer when the planet is in front of it. If it's a large planet, like in these cases, if you look at the brightness of the star as a function of time, you see a very noticeable dip. Note the scale here, that we're talking about fractions of a percent, but with space-based photometry, measurements of flux versus time, you can measure fractional percent precision. But we'd like to measure small planets, hopefully ones as small as the Earth or even smaller, and those actually, the periodicities might be hidden by noise. And again, these are folded. The actual data are spread out in time, not knowing the period a priori. And then there are also stars that just by themselves vary in their brightness very periodically. And one of the ways we're going to study those are with synoptic surveys, which you've probably heard about if you've been here for participating in any of the SAMSI program here. These are digitized robotic surveys that astronomers are undertaking, where we just observe as much of the sky as we can each night and come back to it the same place every few days or a few months. And then we look in different colors. So one of the classes of objects that we're going to be studying with these are so-called Cepheid variables. These are giant stars that are pulsating on timescales of a few days to a few months. And they change their brightness by tens of percent, which is a big deal for a giant star. What's shown here are simulated observations as a function of time in days in 6 different wavebands corresponding to what the Large Synoptic Survey Telescope will be doing in a few years. No obvious periodicity here. So these are just a little less than a year's worth of observation. LSST will observe for about 10 years, and it's going to collect about 1,000 data points spread between these 6 different colors. And this shows what happens in one of those colors once you fold at the right period. And if you can find the right period using a periodogram or something like that, then in fact, the shape of the light curve pops out, and you could indeed see that it's periodic and learn something about the physics from the shape. The 3 cases here are just for different signal to noise levels. These are simulations, obviously. All right, so that's our motivation, why we want to worry about strictly periodic things and study periodograms for them. And then I just want to start the actual meat of the lecture with a cautionary quote by John Tukey, the inventor of the Cooley-Tukey fast Fourier transform, the FFT. So I'm sure the statisticians here know his name. Not so much for formal statistics, but for exploratory data analysis. He invented the box plot. But he did a lot of work in time series. This is a very memorable quote. More lives have been lost looking at the raw periodogram than by any other action involving time series.
He meant lost by the analyst, the statistician.
Yeah,
right?
yeah. Well, yeah, any data analyst. Hopefully the statisticians know how to look at them sensibly, but people like me in astronomy, maybe not so much. Now, I've highlighted here the word raw, okay? And I think that was a very deliberate choice on his part. So the key is that there is useful information in the periodogram, but there are reasons why it's a little complicated to get it out. And so if you understand periodograms, you can spend a lot of time looking at them and learn a lot as a result of your investment. Now there's, I do a lot of different things in statistics, and the statistics literature is always huge, right? I mean, there's so many different areas that statistics works in within the sciences and engineering, and the statistics literature is always vast on any topic, but on time series and spectrum analysis in particular, it's particularly vast. So even this lecture being a survey, it's like just hardly scraping the surface of the vast literature. What's a little frustrating when you try to learn about this stuff is that it's in different literatures in different areas. So in the signal processing literature, it appears under the term spectral analysis of time. I said of time series because there's also spectral theory in math, which has nothing to do with this really. Then there's in applied math, there's applied harmonic analysis, which is something different from pure or abstract harmonic analysis, which is only vaguely related to it, studying structures on groups, but it's related to rotational invariances and things like that. But applied harmonic analysis worries about some of the things that are relevant to statistics. And then within statistics, some of the areas that spectral analysis, that term certainly appears in statistics, but also the terms harmonic regression and trigonometric regression bear on how to understand periodograms. So those are just kind of the main places to go to learn about this. All right, so with that as our motivation and a bit of a cautionary input, here's our agenda. So I'll just have a few slides just to remind you and establish some notation about Fourier transforms. I am going to assume you know a little bit about Fourier transforms. We're not actually going to use too much about them, but I'm going to assume that this will just be a reminder. It's just a few slides. The main part of the lecture is going to be on the magnitude type of periodogram that Schuster invented, the thing that's called the Schuster periodogram, which is for evenly spaced data, and its generalization, which is called the Loam-Scargill periodogram for unevenly spaced data. And then we're going to talk about, if there's time, the area. I've done a little work in this area. I've done more work in the area of periodograms for events, occurrences, in the language of Schuster. So that's our plan. And just to kind of say where we're going, the main thing I want you to take away from this lecture is that there isn't one thing that the periodogram means. The periodogram appears in the same function, the Schuster periodogram or the Loam-Scargill periodogram, appears in different settings in statistics with different assumptions, and as a consequence can be used in different ways for calculating probabilities of things. Like the actual formula for a probability will use the periodogram in a different way depending on what your kind of background assumptions are that have led you to adopt a periodogram. And so the three things are to think of the periodogram as a kind of estimate of the Fourier power spectrum of the underlying signal. That's the kind of most conventional approach, the approach with the longest and largest literature. The second is to think of the periodogram in Bayesian language as the log posterior probability for there being a sinusoid in your signal at a particular candidate frequency. From a frequentist point of view, this would be this comes from those regression perspectives. This would be like it's like the weighted sum of squares of residuals for a periodic model. If we have time, I didn't have time to write the slide, but I'll write one equation on the blackboard with some fairly strong assumptions. You can calculate the likelihood function for a stochastic process. That's a Gaussian process. There's an approximation due to the statistician Whittle called the Whittle likelihood, and the periodogram appears in it as a tool to let you calculate the approximate likelihood function for a Gaussian process. So each of these things lets you calculate probabilities based on periodograms. Here you would calculate like a p-value that a periodic signal is present. Here you'd calculate a posterior probability density, a probability as a function of frequency that if there's a periodic signal present, it's in this frequency range. Here you would calculate the likelihood for the parameters of some Gaussian process like a correlation length or something like that. The periodogram appears in all of these with very different formulas. So it's the same function of the data, but the way it gets mapped to probabilities is different depending on what you're using it for. Okay? So that's kind of the giveaway. So have that in mind as what you should be trying to take away. All right, so the math background. Just to get some ideas in your head that hopefully are already there but might need some dust brushed off them. So the Fourier transform is just a kind of projection operation where you take a complex sinusoid, so e to the minus 2 pi I, and then the frequency here f and time t. That complex, that exponential can be written as sine plus I times cosine, right? So you're looking at the projections of some function onto a sine and a cosine basis and then combining them as a complex number. There's the inverse Fourier transform. This should have been a twiddle, sorry about that. If I take the same function and multiply it by e to the plus 2i, so did I reverse the sine and cosine? Yeah, this is cosine and sine, I'm sorry. Flip the sign here, that flips the sign of the I term if this was a sine. You get back the original function. Sometimes you'll see this written as some f operator. This is an integral operator. F operating on g gives you the transform. F to the minus 1, this version operating on the transform gives you the original function back. So g and g twiddle are called the Fourier transform pair. And then here are some notable ones. I stole this from a nice note online by Jake Vanderplas. I'll have some more comments about that later and show you where to find it. So the Fourier transform of a sinusoid is a pair of delta functions around the origin. If you're looking at real valued signals, you only need to look at the positive half. But that's kind of the point of Fourier transforms, is they separate something that's a harmonic sum of sinusoids into just identifying what the periods are, what the periods of those sinusoids are. That's what these delta functions are telling you. A Gaussian, if you Fourier transform it, it's another Gaussian. The narrower it is in one space, the wider it is in the other. The Fourier transform of a top hat is a sinc function, sine x over x, so it's something that's oscillatory, but with the amplitude of the oscillations damped as you move away from the peak. And then there's this function that we'll see why it's important in a few slides, called the Dirac comb. So this is just a sum of periodically spaced delta functions going off to infinity in both directions. So this is kind of the most periodic signal of all, sort of. It becomes another Dirac comb in Fourier space, but with a reciprocal period. Okay, and one of the most important things about Fourier transforms is the convolution theorem. The transform of a convolution is a product, so if I take some function f and convolve it with some function g, the Fourier transform of that, the result of that integration, is just a simple product of their separate Fourier transforms. And this has a kind of converse, which is that the Fourier transform of a product is just a product of Fourier transforms. So the convolution theorem is both of those things. So hopefully you've seen that before somewhere, but this was just a reminder of those things. All right, so now let's talk about periodograms for this what Schuster called the magnitude case, where I'm measuring something. I'm choosing the times at which to measure it, at least to some degree. Astronomers don't always have a choice, but we pick a time, and we observe and we measure some real valued magnitude. The most conventional way that periodograms arise in what one might call periodogram-based spectral analysis. And here's the underlying idea. A periodic signal, which you could write as a sum of harmonics of sine waves, a period twice a frequency, twice the frequency, 3 times the frequency. Any periodic signal can be written as a sum of harmonics like that. So a periodic signal could be recognized by looking for delta functions in the spectrum of the signal. Of course, we don't have the actual signal. We have some kind of measurement of it with noise and only at some times. So the idea is we'll try to use our data to estimate the signal's power spectrum. Once we estimate the spectrum, then we'll try to find where there are delta functions in it, and those will be the periods, at least the candidate periods. And I should have said something earlier. I should have defined power spectrum is just the squared magnitude of the Fourier transform. Right? So this thing in general is complex. It has a real and an imaginary part, and you just take the squared magnitude of those to get, that's the power spectrum. All right, so that's the idea. So the periodogram is basically the power spectrum of the data. So I'm going to write the data is the underlying signal, some function, some continuous function of time that we're just probing at a few discrete times, or not necessarily a few, but at some finite number of discrete times, and with some additive noise. And when the time comes, we're going to assume this noise is white and Gaussian for now. And so the power spectrum is just a kind of some version of the Fourier transform. Instead of the integral of f times sines and cosines, it's the sum of the data times the cosines and sines. So this is just that formula that you saw from Schuster, where this was just the x coordinates of all those of the sum of those unit vectors, and this was the y coordinate. And then you sum them, you square them and sum. And I just want to note I've chose a certain normalization here. Different books and different papers will sometimes have different factors out front. This is just something to be aware of when you're looking in the literature. So when the data are sampled evenly in time, so that the times are all separated by some fixed constant time delta t, if you will, then this thing is called the Schuster periodogram. When the data are unevenly sampled, then something very much like this is called the Lohm-Scargill periodogram. What's slightly different is that you introduce a phase, and there's you try to kind of optimize for each choice of frequency what that phase is. And we'll say a little bit more about why that complication arises later. But in the end, it's the same thing. It's for some chosen basis, in this case with some ideal optimized phase adjustment. For some chosen sine and cosine basis, I'm just projecting the data. Basically, what makes the Schuster periodogram nice is that with evenly spaced data, sines and cosines are orthogonal to each other. If the data aren't evenly spaced, then they're not. And so, but if you introduce just the correct offset in time, then you can make them kind of as orthogonal as possible. And that makes the statistics nice. So that's the difference. Okay.
In your very first historical slide, you had a square root to make it into a distance.
Yeah, so
Doesn't matter.
I haven't sorted that out, whether the actual distribution he used was what we call the same p-value distribution. That's a good point. I don't know. Okay. All right. So the idea is, think of this as having something to do with the spectrum of the signal. It's really a spectrum of the data, not a spectrum of this function f. And we have to worry about that distinction if we want to try to make some statements about the spectrum of f from the spectrum of the data d. So there's going to be a bias and variability. There's going to be error in this power spectrum estimate, which as statisticians we like to separate into bias and variability. Bias is how much the expectation is away from the truth, and variability is how much it varies in repeated sampling. So the idea is that the data are not the continuous function. The data are discrete values of the function. So we talk about the data being windowed. That the process from going from the continuous function to the observed data is what's called windowing. It's choosing the times and also choosing the duration over which you have the function. So we've kind of, you could think of it, and we'll say more in a next slide, is that you've kind of multiplied the continuous function by something that's restricting it to a time interval and then picking out just certain discrete times. So I'm not looking at the power spectrum of the function f, I'm looking at the power spectrum of f times this kind of windowing thing. But you now have your memories refreshed from the convolution theorem that the power spectrum or the Fourier transform of a product is going to be a convolution of Fourier transforms. So that gives you some intuition already in that you shouldn't expect the spectrum of the data to really duplicate the spectrum of the underlying function f. So to do statistics, we have to introduce some kind of null hypothesis. And so that's just going to be that there's no periodicity present, that there's only noise. And for simplicity for now, we'll say that the noise is independent and identically distributed. And then it turns out that with n data, there are n over 2 values of frequency at which you can evaluate this, this power spectrum and get independent values of p under the null. Those are called the Fourier frequencies. Those happen to also be the frequencies that are returned by the fast Fourier transform or the discrete Fourier transform. And the point of them is that they're statistically independent. And again, this is something that follows from the orthogonality of sines and cosines on a uniform grid. When the sampling times aren't uniformly spaced, things are more complicated in terms of how many of these are statistically independent, but it's a similar order of magnitude. Does anybody have any insight into why it's n over 2 and not n? So you've measured n quantities, and we're calculating this power spectrum, and what the theory, which we haven't worked out here, tells you is that you only learn about n over 2 values of the power spectrum when you do this. Okay, so what's the relation of the power spectrum to the Fourier transform? It's the squared magnitude. So there are phases that are lost when you're calculating the power spectrum. And so the other n over 2 things that you could learn from the data if you were interested in them are the phases of the components at each of those Fourier frequencies. So it's not that you've lost, it's not that there's somehow information magically lost in the data. It's that by choosing to only look at the power spectrum, you've thrown out half of the information in the data. But hopefully it's the information that's most relevant to saying whether there's a frequency present. I mean, the intuition is that if I just want to say whether there's a frequency there or not, I don't care what its phase is, what the shift is in time. So hopefully that information is not useful. We'll see in a few slides that there are settings where it actually becomes useful.
In practice, if you care about the precision of these frequencies, there's no harm in evaluating it 3 times more frequencies than that, just to keep it smooth.
Yes, as long as you, so what the issue is that if you then try to find the peak and assess the significance of it, you now have to account for the fact that instead of having n over 2 independent samples from the null, you now have 3 times n over 2 dependent samples. And that's not a trivial thing to do, but you can do it. Actually, the easiest way usually is just to simulate it. But that's the complexity. That's why, at least for the theory, it's easiest to focus on the Fourier frequencies. Okay? But that's a great point. We'll see why that's important in a minute. Okay, so bias and variability. So it's kind of obvious that this power spectrum estimator actually is not good in terms of variability. So we've learned from statistics not shown here that you can get n over 2 independent values of it, right? But that's proportional to n. So the more data I have, the more periodogram ordinates I'm estimating from those data, proportional with n. So as a result, since I'm trying to estimate a number of quantities that grows with n, there isn't much averaging going on to beat down variability, and the periodogram at the Fourier frequencies stays variable as n goes to infinity. So As a result, it's an inconsistent estimate, right? For a consistent estimator should become less and less variable as the data set grows in size, and it should converge to the true value. Here, it varies around the true value, at least up to the bias, but the variability doesn't shrink to 0 as the sample size grows, because the number of things you estimate also is growing in number with the sample size. So that's kind of obvious, and one might hope that some kind of local smoothing could hopefully get rid of some of that, and that is indeed true. But more troubling and more complicated is the bias. We're not looking at the power spectrum of F, we're looking at the power spectrum of D, and D is related to F through finite sampling and adding noise, and the convolution theorem already gives us some insight into how that might be a problem. The fact that you only have the function at discrete times over a finite interval biases the shape of the periodogram. And so I try to show that in some plots here that I stole from Jake. So he has this long note on GitHub called Practical Loam-Scargill. And there's a very nice introduction to Fourier methods and kind of a concise summary of what you need to know about Fourier transforms to understand periodograms. The statistics part of the note, it's about 75% right, but some of it's not really right. So if you go there, and I'll give Eric these slides, this is a live link, but it's a useful note, and he last updated it 5 or 6 days ago, so it's a work in progress, and maybe the statistics part of it will improve. But anyway, it's a very nice plot. So we're going to write that what we observe, so ignoring the noise, the part of the data that's coming from the signal is the original function times a box that's limiting us in duration, and then times a Dirac comb that accounts for the discrete sampling in time. So remember, the Dirac comb goes off to infinity, so we need the box times the comb to get discrete sampling over a finite interval. So you've already seen some Fourier transform pair. So you already saw that the transform of a box is a sinc function. This is just some example signal F that Jake made up that has 4 harmonics in it, 4 sinusoids. And so its Fourier transform shows up as 8 mirrored delta functions, right? So if I multiply this continuous function by this box, so this is as if I had noiseless data that was a continuous function measured at every point in some finite interval, then the transform of that is this rather than this, because of the windowing by the box. So instead of each of these delta functions, I get this sinc function with this ringing at each of those delta functions. So that's what the duration does to you. The Dirac comb, so here he's looking at a Gaussian signal, multiply it by a Dirac comb, and so you just get Gaussian weighted delta functions. Well, remember, the Fourier transform of a Gaussian is another Gaussian. The Fourier transform of a Dirac comb is another Dirac comb. If I convolve these, right, there's a product in this space. The transform of the result is the convolution of its transforms. Convolve the Gaussian with this, and I just get a bunch of Gaussian superposed. So when I look at the Fourier transform of noiseless data, but that's been sampled over a finite time with evenly spaced samples, then I'm going to get something that involves both of these effects happening, this kind of broadening of the lines due to the finite, the discreteness of the sampling, and then plus this ringing that happens from the duration cutoff. So both of those effects bias the periodogram estimator. Exactly what they do depends on the frequency of the signal. And the terminology that's used for the effect I'm about to describe is called spectral leakage. So what I've done here is I've looked at a sinusoid, 1,000 samples, so not a huge number. This was motivated by an audio problem, so this is a common audio sampling rate. Fairly weak, signal to noise of 5 with white noise. But I put in, I'm looking at the power spectrum, the Schuster periodogram at 2 different frequencies. One of them is one of the Fourier frequencies, one of those n/2 independent frequencies, the magic frequencies that come back from the fast Fourier transform. And when I look at that, all the power ends up in a bin at that frequency. But in this case, I picked a frequency in between the 2 Fourier frequencies. And when I do that, then the power, what's said is that the power leaks. It leaks into neighboring frequencies. That is, if you're focusing on just what's statistically available in terms of independent pieces of information, you have to focus on frequencies that might not be the actual frequency of the signal. And if you try to expand a signal of one frequency in a basis that doesn't include that frequency, the power has to be spread out over many frequencies. So, so that's just one example of how the power spectrum can get biased. And then there's a huge literature on how to deal with these biases. And there's kind of 2 main branches of it. One of them, which mainly addresses variability, so it's bias and variability, is periodogram smoothing. It also helps in addressing this kind of ringing. So you see in this spectrum, the original, the signal spectrum has 4 + 4 peaks. This new spectrum, just due to the finite duration windowing, has lots more peaks due to this sinc function. So, but if you were to smooth this, you could get rid of or at least reduce the amplitude of those. So there's a whole literature on smoothing to reduce variability and to handle some of that windowing effect. And then there's also a literature on data tapering, which are clever ways to multiply the data before you take the power spectrum that can address some of the things like leakage and things like that. So this is just a vast literature on ways to try to handle leakage, variability, the windowing effects. And if this were a real, like if I were an engineer giving you a time series course, we'd spend several lectures on those things. Those are like a main topic of spectral analysis. All right, so now we're gonna.
Could I just
yes.
mention? I'm gonna ask you to guess. How many astronomy papers in the last 30 years use tapering with periodograms?
Use tapering?
Would you say?
I would
Tens of thousands, thousands, hundreds, or tens?
I would say, based on discussions with Jeff Scargill, who loves tapering, that it's probably tens.
Right. It's about 20. It's about. Excuse me. It's even less than that. In any given year, it's about 5 a year. And periodograms are used much more than 5 times a year in astronomy. What I want to say is that despite Jeff Scargill's attempt to promote it, despite the fact that every textbook taught in every engineering class or economics class about time series analysis always has chapters on tapering, astronomers don't do it. Until 2000 and even today it's gone up to 10 per year. It's pathetic how astronomers don't know tapering. And they think, remember John Tukey, they look at raw periodograms. So how many lives have been lost?
Right.
So I don't
Smoothing is used more, but mostly just because it comes out. There's, there are routines in SciPy and stuff that do it. But and the X-ray astronomers know about smoothing, but not tapering.
Excuse me. If I understand, for extremely long durations, tapering is not important.
Yeah.
It's the tapering is for the short duration aspect of leakage. It doesn't address the cadence, which is a separate.
Yeah. So it doesn't deal with this. The
it
idea.
Doesn't deal with aliasing. It deals with leakage.
Right. So as this gets wider, these get lower, but when you taper, the idea is that instead of having this be a box, it's something with smooth edges, and that makes some of these ripples go down. That's the idea. All right, now we're going to take a different perspective. So the underlying idea there, which has kind of dominated frequentist use of periodograms, is to think of the periodogram as an estimate of the signal spectrum. Now we're going to take a different approach, and kind of to put it crudely, the way I would say this approach, the way I would characterize this approach is that it says, well, wait a minute. I'm saying I'm looking for a periodic signal. That means I'm saying I know its spectrum is delta functions. So let's forget about trying to estimate the power spectrum. I'm asserting that I know the shape of the power spectrum. It's a bunch of delta functions. All I need to do is to estimate where those delta functions are and how big they are. Okay. So that's kind of the way I would kind of characterize the difference between these approaches. This one is saying, well, you're interested in periodic signals. You know it's got to be a delta function, so assume that at the outset. And stop worrying about trying to correct the shape of the thing to make it look more like a delta function. You know it's a delta function. You don't want to find an estimator and look for delta functions in that estimator. You want to assume the spectrum is a delta function and use the data to constrain where those delta functions are and how big they are. And the way you're going to do that is by building a time domain model that has delta functions in it. And so this approach to looking at time series, there's a frequentist branch of this. It's mostly related to that stuff that I called that I mentioned, harmonic regression, trigonometric regression. It's very much related to kind of least squares, weighted least squares estimation and regression. And so let's pick it up there. Let's see.
We can stop now.
You want to stop now?
Oh, I should correct this. I apologize. I looked for the words tapering and periodogram, came up with 10 a year. Tapering in power spectrum is 50 a year, and most of it in the last decade, even though tapering has been widely promoted since the 90s. I mean, it's older than that. It goes back to the 60s, I think. But the textbooks have all been teaching it for 30 years. And astronomers are only using it the last decade 50 times a year. So I apologize for scorning astronomers at 10 a year. But, well, thank you, Tom. This is a good juncture to have a break, a bathroom break.
So just to recap, so we started out by thinking of the periodogram as an estimator of the spectrum. Now we're going to give up that perspective. We're going to assume that we know the spectrum, at least its shape, that it's going to be a delta function, that it's a periodic signal. So we're going to write down some possible periodic signals and then just do some statistics, that kind of a regression type viewpoint. So, and ask what we can say about whether there's that periodic signal there or not, and how to estimate its period, and so on. So basically, we're going to look at it as a least squares problem, and I'm going to adopt the Bayesian perspective here. And so this is a recap of stuff that probably you're all familiar with. I think I may have showed some of this stuff last semester for those who took that version of the course. But anyway, so the idea is that you have some data that are measurements of some function. It could be of time or space or some vector. And you have some model that has some parameters theta for what that function is. And there are a bunch of sample points that you have. I'm going to use the notation f sub I of theta to be the parameter dependent value of the function at a particular node that you're measuring. And so the data are the function plus some additive noise, and we're going to assume white but independent but heteroscedastic noise. So ID but not IID. And the idea is we want to learn about the parameters, or we might have rival models with different parameters and we want to be able to compare them. So I'm just going to go through this quickly because I'm assuming you're familiar with this stuff. So there's a likelihood function. It's just a product of the Gaussians. The nice thing about Gaussians is that the things in the exponents add. I'm assuming for the moment that the sigma i's are given, so I'm just dropping them because the likelihood, they'll just drop out in Bayes' theorem. But we'll worry about, I'll say one word about that in a slide or two. So we have a sum of the squared residuals. Astronomers like to call that chi-squared. It's probably not a great symbol for it, but it's not always something that's chi-squared distributed, but that's what astronomers call it. So if you're familiar with doing chi-squared fitting or weighted least squares fitting, the likelihood function is just e to the minus that function, sum squared residuals over 2. And then from a Bayesian point of view, the way you go from a likelihood to a probability is you multiply by a prior, something that makes it a measure over the parameter space. So I'm writing the prior as pi of theta. For those of you, I think everybody here is familiar with Bayes stuff, so I'm not going to say too much more about it. We won't worry about this. So what you need to do is explore this thing as a function of theta. It's something that was simple as a function of the data, right? It's Gaussian as a function of the data. But as a function of theta, depending on how theta controls these f's, it can be arbitrarily complicated. So exploring this thing as a function of theta often is challenging, but sometimes not, as we'll see in a minute. If the noise level is uncertain, you could include parameters for the noise. Like you might say that the sigma i's are actually only the relative sizes of the noise, but there might be some unknown multiplier, call it alpha or something, and you could introduce that as a parameter. If you do that, then you've got to keep terms that I've left out here. You've got to keep the sigmas in front.
And some people, you put an additive term in as in a scatter.
You mean sigma? Yeah, yes. That could be a parameter. So then this would be a 1 over sigma squared square root.
Brennan Kelly's famous model from 2007. That's fairly widely used in hundreds of papers in astronomy.
Yeah.
Is an additive.
Yeah, it's analytically it's not so nice, but that's what we've been using in exoplanets for 15 years. Is the same kind of thing.
Well, I guess what I was thinking is, I think in statistics jargon parlance about regression, I think it's called equation scatter. That would be the intrinsic scatter of the stars or the galaxies or the quasars that you're looking at would be an additive element, and then we have a heteroscedastic scatter that is associated with the measurement process, which is this sigma sub I here, and astronomers have a long-standing tradition of considering only sigma sub I as the only source of scatter, which is the one here. But sometimes they add an equation scatter as well, and there's several least squares type solutions, and then Brennan Kelly suggested a likelihood-based solution. He wrote a complicated likelihood down for that problem.
Okay. All right, so here's an important case, which is going to occupy us for several slides with a little linear algebra, but it's probably something you've all seen before. And that's a case where what you have are what's called separable nonlinear models. And I learned this math back when I was a graduate student in the 80s. And I felt like this had to be such a well-studied class of models that it had to have a name in statistics. And for probably 15 years, I could not find what the name was. I'd ask statisticians, they wouldn't know. Maybe some of you will say you knew this. But this term, it turns out I only found by accident. It's in the operations research literature that this class of models has a specific name. Okay, so this is what is meant by a separable nonlinear model. It has some parameters that can be divided into two groups. There are what are called linear amplitudes. So these are vectors. So I'm going to denote each amplitude with some subscript alpha. And then there are nonlinear parameters psi. And the idea is that the function, the underlying function, is a linear superposition of some number, capital M, of nonlinear component functions, G sub alpha. And I'll give you some examples to make this concrete in a moment. So alpha is an index over the components. I is an index over the data. So these are different dimensions. So there might be M components, nonlinear components in the model, each with a linear parameter. And then there are N data. So just to define the terms, linear or nonlinear refers to how the data depend on the parameters, not how this thing behaves as a function of x. We'll see what I mean by that in a moment if it's not clear. But okay, so does anybody know if there's a name for this in statistics other than linearly separable nonlinear models? Anyway, that's the terminology. So here are some examples. So polynomials are a case where there are no nonlinear parameters. So here's a cubic polynomial. This is a function that's not at all linear in x, but it's a linear model because it's linear with respect to the parameters, which are the a's. Right? Or I might have it in a different basis. I think these are Chebyshevs, or it could be any kind of basis. Sinusoids are a case where there is one nonlinear parameter. So if I write f as some sinusoid with some amplitude, some frequency omega, and some phase phi, this function here depends linearly on a, but nonlinearly on omega and phi. But I can just use a trigonometric identity to reparameterize it. Remember, a cosine of a sum is a sum of cosines and sines, right? So I can write this as a1 cosine omega x and a2 sine omega x, where a1 and a2 involve sines and cosines of phi. This is like a sine phi. No, this is a cosine phi, and this one is a sine phi, maybe with a sine. So I would call this G1, and it has one nonlinear parameter omega, and this would be G2. The second component would be the sine. It has the same nonlinear parameter, but it's a different function, right? So two components, but one nonlinear parameter, and two linear amplitudes. What started this field in Bayesian statistics was a paper by Ed Janes that tried to generalize periodograms to worry about chirping signals where there's a frequency that's growing in time, or in this case, space. So instead of just omega x, there's also an x squared term. So as x grows, the instantaneous frequency is growing. Here's the instantaneous frequency. So I can do this same kind of trick here. There's two linear parameters, but now there's two nonlinear parameters. The frequency at some reference phase, and then the rate of change of the frequency. So this can be arbitrarily complicated, and we'll do another example or two later. So that's the idea we want to work in this class of models. So the Janes-Brett-Horst algorithm or framework, it doesn't really have a widely recognized name, but it's from papers by the two of them, Ed Janes, a physicist, and Larry Brett-Horst. Ed Janes was a pretty prominent physicist, probably best known now for introducing Bayesian ideas into the physical sciences, but also known for a lot of work on kind of quantum electrodynamics, quantum theory, and especially for statistical mechanics, the maximum entropy method and maximum entropy methods for data analysis. And all of his graduate students worked in physics, except his last graduate student, Larry Brett-Horst, is only one to work on statistics, and one of his best known students. And so the algorithm is named after them. There's a free book online where it's basically Larry's thesis published by Springer that describes all of this. It's very closely related to least squares or singular value decomposition. So this will look similar, but except that it inserts these nonlinear parameters and worries about what they do. So our goals in problems with this structure would be, we might want to focus on the nonlinear parameters. Maybe some of the physical questions of interest are about them. We might want to estimate the amplitudes, or both of those jointly, and how they're related. We might want to compare rival models with different components and different amplitudes. Why this is nice is that the log likelihood function, so the argument of the exponential, is a quadratic form in the amplitudes. So it's d minus the sum of the amplitudes times the g's. I'm suppressing the x dependence by making d a vector and g a vector. So it's a column vector where the top one is d evaluated at the first time, the second is d evaluated at the second time. So Those are vectors in n-dimensional space. There are m basis vectors, if you will, g, for each choice of the nonlinear parameters. And I'm basically projecting d onto this space, onto the space spanned by the g's, basically. So if I square this thing, it's going to have quadratic and linear terms in the alphas. That means I can complete the square. This thing will stay Gaussian. It will become a correlated multivariate normal in the A's, and that's something that I can integrate analytically. So that's why this class of models is interesting. If there are m components, I can get rid of m of the parameters analytically. And remember, what makes Bayes hard is that you have to explore that chi-squared thing as a function of all the parameters. But for this class of models, there's a significant chunk of the parameter space where you can handle the parameters analytically. So what we do here is we're just squaring. So multiply this by itself. D gives a d squared, just the amplitude of the data vector. There are two terms that involve products of the A's and this function here, which I'll talk about more in a minute. And then there's the projection of the data onto the basis vectors. So this thing here, the notation is meant to be attractive to physicists. It's the symbol that's used for a metric. It's the dot product of the two basis vectors onto each other. So if your basis vectors are orthogonal to each other, this term vanishes, and then the cross parts of this term vanish. You only get a alpha squared instead of a alpha a beta. And so that's what we'd like. We'd like to have models that are orthogonal. Of course, the models of interest may not be, but so all the math in the James Bredhorst algorithm is to change bases to a different basis. I've called it H here. It's just going to be a rotation and possibly a squashing of the original G's. So I'm writing each G as some superposition of some new basis H, which is equivalent to writing H as a linear superposition of the G's, just with this A matrix inverted. Then I can rewrite F in terms, which we've expanded in terms of our initial model basis functions. I can evaluate it with different amplitudes times this new orthogonal basis. If you go through some of this linear algebra, for this to be orthogonal, you need this matrix that transforms H to G or G back to H. You need it to basically be a square root of the original metric. So you start with a basis in your n-dimensional data space that's not orthogonal. So each of those vectors has a non-zero dot product with all the other vectors. Write a matrix of those dot products and take the square root of that matrix. This is the Cholesky decomposition, the matrix square root. When you do that, then each factor of those square roots is a rotation that produces a new basis that spans the same subspace of the data space, but it's now orthogonal. So it's just linear algebra, and it just involves a Cholesky decomposition, or actually it's a little better conditioned if you use a QR decomposition, but it lets you write the quadratic form in terms of the new amplitudes on that new H basis function as a complete square. So just B minus some projection of the data onto the B's, where this B hat is the best B vector. It's literally just the projection of the data onto the H vectors. Now, these vectors, your original G's in this space, they're actually changing depending on what your nonlinear parameters are. And as a result, so are these projections. So you have to worry about this, how this A matrix depends on your nonlinear parameters like frequency or chirp rate. And you actually have to rotate for each set of parameters. A Jacobian appears because of you changing from A to B. But it's all pretty straightforward linear algebra. You get this complete square in B, so this is easy to integrate. And what you're left with here is the squared sum of residuals, D minus the projection of the D's onto the basis. So you're looking at what's the part of the data that don't lie in the subspace spanned by the model. And then for each choice of your nonlinear parameters, that it's how much misfit there is from that subspace determines what appears as in the exponent for the joint posterior distribution. So when you marginalize, this disappears, marginalize over the b's, and you just get a posterior density for the nonlinear parameters like frequency. And it's just e to the minus the sum squared residuals projected onto the orthogonalized basis. If you don't know the noise level, you can deal with that. I'm not going to talk about that in this lecture. All right, so I think so I just rewrote that here. The residual is just the squared magnitude of the data minus the best fit minus the projection into the subspace spanned by your models. That's what this thing is here. So this is the only thing that depends on the nonlinear parameters. So that's something like a sufficient statistic. It's basically just the sum of the squared projections into that space. All right, so that was very abstract. It was linear algebra, not very challenging, but still kind of abstract. So this was the insight that Ed Janes had in this paper that was kind of surprising and very cool. He said, okay, so let's do this. Let's adopt a sinusoid model. So there's two linear parameters, the amplitudes, one nonlinear parameter, the frequency, and the basis functions are cosines and sines. Okay, let's throw that into this algorithm. So we're going to get an exponential once we eliminate the amplitudes. We're going to look at the marginal posterior distribution for frequency. It's going to depend on this sum of squared residuals as a function of the frequency projected onto the space. Now, if our sampling is at equally spaced times, then when there are lots of data, the sine and cosine basis is already orthogonal. I don't have to do anything fancy. And when you do that, this sum of squared projections is just the Schuster periodogram. So the Schuster periodogram appears here without us we're not attempting to estimate the spectrum. We're saying, I know the spectrum is delta function. I just don't know the frequency and the amplitude and phase. And the Schuster periodogram gets handed to us, not as a spectrum estimator, but as the log of the marginal posterior for the frequency. Totally different interpretation, totally different way that it appears in the probability equations. Instead of appearing in a Rayleigh distribution, it just gets exponentiated. So that's what happens with equally spaced data. With unequally spaced samples, so this was an old paper of Ed Janes, then his student Larry Bredhorst handled this case about 15 years ago and showed that this becomes the Lohm-Scargill periodogram when you have unequally spaced data. So you didn't have to try to introduce it as a spectrum estimator. If you assume the spectrum was delta functions, that is that the model was sinusoidal, with a single sinusoid, then you're handed the Lohm-Scargill periodogram.
Does this also resolve the issue of multiple hypothesis tests if you have a...
Yeah, I'm going to talk about that.
Thank you. Okay.
Okay, so this thing is a function of this continuous unknown parameter omega. There's nothing from the Bayesian point of view that worries about whether this is statistically independent for different values of omega, right? Or I'm not thinking about how this depends on how the S at some given frequency would fluctuate if I had different data. I'm taking my data as given, and I'm asking, what is the likelihood for omega? So there's no notion of Fourier frequencies that appears here. We're interested in this thing as a continuous function of omega. So let me remind you, let's go back here. So when we think of the periodogram as a spectrum estimator, we want to focus at independent frequencies, at the Fourier frequencies, and we saw that if the true frequency was at a Fourier frequency, all the power was there. was at 1 bin. But if the true frequency was between Fourier frequencies, which it almost will be, then there's this so-called leakage. Okay. What happens if you don't focus your attention on the Fourier frequencies? And from the Bayesian point of view, there's no reason why you would. Right? You're interested in this thing as a continuous function of omega. So these are the same, this is the exact same data set. And what I'm showing you here is the Schuster periodogram as a continuous function of frequency. In this case, when the frequency happens to be at a Fourier frequency, the points show where the Fourier frequencies are. But you see that actually there's lots of structure in this thing. If you just look at the Fourier frequencies, you just see one bump here and everything else. This is now on a log scale. Everything else is down near 0. But if you move yourself away from the Fourier frequency, the shape of this curve, of the continuous curve, actually isn't qualitatively different, right? If you think of the periodogram as a spectrum estimator, its statistical behavior is very different if your signal is at a Fourier frequency or not. But if you think of the periodogram as the log posterior for the frequency, it's just a continuous function of frequency, and there's nothing special about the Fourier frequencies. Also, this is now in this case, a logarithm of the probability distribution for a frequency. It's not the power in the original signal at a given frequency. I'm saying that the spectrum is a delta function. It's where is that delta function? And so what this structure is telling you is that when you have finite sampling and a finite interval, there's uncertainty in the frequency, and the uncertainty is somewhat oscillatory. Now remember, this is the periodogram, the power spectral density, but the posterior for the frequency is the exponential of this, divided by the noise level. When you do that exponentiation, you get these marginal distributions over here. So though there is this structure here in the periodogram, it gets exponentially damped away. So in comparison to smoothing or tapering methods, the idea here is that if you really believe there's a periodic signal, what you should be doing is not some linear operation like smoothing the periodogram or tapering the data. It's a nonlinear operation. Exponentiate the periodogram, and the resulting function tells you where the frequency is. Okay. So it's a very different kind of operation, just by taking a different perspective on what question I want to ask. Right? The conventional perspective is start by asking what's the spectrum, and then take a look at your estimated spectrum and try to find evidence of delta functions. This is saying, I think it's periodic. If there's something periodic, then the spectrum has to be a delta function. I just want to know where's the delta function. Very different perspective. So what are some of the new features of this? So this is what I've already harped on. It's not a power spectrum estimator. It's something that tells you where the frequency is if there's one present. There's no special role for the Fourier frequencies. There's no leakage is not an issue. There's as much leakage in the sense of structure in the log posterior at Fourier frequencies or non-Fourier frequencies. And the side lobes are not something you want to get rid of. In low signal to noise, the side lobes actually tell you about the uncertainty in the frequency. You don't want to smooth them away. They are actually telling you what the data tell you about the frequency. This is what starts speaking to the question Eric asked. And the question is, most directly, the periodogram tells you where there is a frequency, if there is one. But then you could ask, is there evidence for there being a periodic signal? To do that, if you know about Bayesian inference, you know you need to know the marginal likelihood, the integral of the likelihood over all of the parameters. So we just did the integral over the amplitudes. We could do that analytically. Now, to get the marginal likelihood, which tells me how strong the evidence is for a periodic signal, I need to integrate over frequency. So that's a totally different operation than from the kind of conventional frequentist approach, where instead I look at the Fourier frequencies and I optimize over them, and I pick one of them, but I somehow have to account for the fact that I looked at all the others. You don't have to worry about any of that kind of stuff. The marginalization, the integration is what takes care of the multiplicity of possible frequency hypotheses. Basically, when you integrate the likelihood function, which is e to the periodogram, that integral is approximately the peak times the width divided by the prior range, because there's a prior factor in front, and the value of the prior is roughly 1 over the prior range. So you get a kind of how well you've resolved the candidate frequency divided by the size of the frequency space. So the size of the frequency space enters, but it enters literally as the size, the maximum frequency minus the minimum frequency, not as the number of frequencies that you looked at. And so there are no issues when you get into the case of non-equally spaced samples. There are no issues of having to worry about which frequencies are independent and to what degree they're independent. You just have to integrate the same as you would under the equal sampling case. There's nothing qualitatively different.
How do you decide how big is big? Like once you've computed this statistic.
Right, it's just, so this number, if you integrate the marginal likelihood, you have to integrate it also for the competing hypothesis, the null, which just has an amplitude and a noise. So it's literally the ratio of those two things is what's called the Bayes factor. It's an odds in favor of there being a signal or not.
Oh, and then is there some known thresholds if you have a Bayes factor above some point?
No, so just like there's no p-value threshold, right? I mean, there are conventions that, p-values, depending on your literature, like in sociology, p-values, or biology, p-values of, 1% or 5% might be enough. In physics, we tend to not believe things till they're 10 to the minus 3 or 10 to the minus 5. But similarly here, except that they're easier to interpret. Basically, what you tend to find is things that have a p-value of order of percent tend to have a Bayes factor of order 1.
But so you still have this issue of determining how significant something is.
Yes, absolutely.
Doesn't get around that.
No. I mean, you want to worry about that. That's what you want from this, is a number that tells you how strong the evidence is. But you don't want that number to depend on things like, remember, there's n over 2 Fourier frequencies that are independent. Actually, the choice of those is arbitrary, right? The fast Fourier transform picks some for you that are handy numerically, but I can shift that by any amount that I want. But if I do that, I'll change where the peaks are. So you don't want arbitrary choices like that to influence your result. But if you're integrating under the curve, there's that doesn't even enter anymore. The other thing is, and this is a cool point, is that we got this Schuster periodogram to appear by assuming a time domain model of a single sinusoid, right? So this is saying that a periodogram is only optimal for a single sinusoid model, right? But a periodic function might not be well described by a single sinusoid, right? If there's just one period, we still might need harmonics, right? And then the Schuster periodogram is no longer optimal, and this framework will give you something else. So let me just elaborate a little on these last 2 points. Here's the frequentist use of the periodogram, right? So there's some continuous Schuster periodogram, but only some subset of those are independent. So if you want to easily calculate a p-value, you focus on those. There's a null distribution. It happens to be chi-squared 2. Basically, the sum of the sines is a normally distributed quantity. The sum of the cosines is a normally distributed quantity. When you sum 2 of them squared, you get a chi-squared 2. So that's the null distribution. So each of those maps there. And then there's a largest one. So you pick the largest one, and then the p-value is just the tail area, right? What the Bayesian approach does instead is it takes the periodogram and it exponentiates it firstly, so that it's now a probability distribution over frequency. I changed from omega to nu here, sorry. So that exponentiation beat down, this is a very noisy example I did, but so the side lobes don't totally get beaten down, but beats them down somewhat. And then what you need to do is look at the continuous function and integrate under it. So basically the area under this curve compared to the value you'd get just for the noise model is the odds in favor of there being a frequency. This is just a side comment. There's nothing in principle in frequentist statistics that says you can't integrate things. So this is an interesting article. It's in the ASTRO literature. It's in the SCMA, one of the SCMA papers, where Peter Bickel and John Rice have a paper where they integrated a statistic and looked at its distribution from a frequentist point of view. They integrated the log of the periodograms. This is not something you'd ever do from a Bayesian point of view, but it was something for which they could calculate some statistical distributions. But it's just the point that in some sense you have a lot more freedom in frequentist statistics. It's not nearly as principled an approach to inference. So they kind of stole this idea from Bayesian inference that integrate rather than optimize. And it had some virtues in their case. It's rare where you can actually do anything theoretical with that, but they could. All right, so I said I was going to harp on those 2 points. So one of them was addressing Eric's question, dealing with multiplicity. You integrate rather than maximize, so it gets handled very straightforwardly. And the other point is that it's only optimum. The periodogram, the Schuster or Loam-Scargill periodogram, is only optimal for single sinusoids. So what happens when there are two sinusoids, kind of the simplest case? I don't mean two harmonically related sinusoids, but let's imagine there are two periodic signals. So one of the problems that motivated Schuster was the 11-year periodicity was obvious, but people were wondering, is there a 26-day periodicity due to the rotation of the sun and the sunspot number? So those are two periods that aren't harmonically related. Or you might, I'll show you an example in a minute from industry, from audio engineering, where you try to want to resolve two closely separated but distinct sinusoids. So what happens if there are two? So there's two different frequencies, should be a parenthesis here. And then I'll break each one into two amplitudes and a cosine and a sine. So there's 4 amplitudes in total, 4 model components. And then I'll do the Jaynes-Bretthorst trick where I now have 4 unit vectors in my n-dimensional data space. And I'm going to use some linear algebra as a choice of frequency. Of the 2 frequencies, I'm going to orthogonalize and project the data onto them, and then integrate out the a's. The resulting function is going to be a function of the 2 frequencies, right? Not just of one frequency. You could write it in terms of the 2 frequencies, or sometimes I like to write it in terms of one of the frequencies and a splitting. If I'm interested in 2 frequencies that might be close, this is just sometimes a more convenient way to handle this numerically. Delta omega is omega 2 minus omega 1. And I call the logarithm of this thing, in analogy to the periodogram, I call it a doublet periodogram. You could imagine a triplet if there were 3 close frequencies. So if you go through the math analytically of what comes out of the Jaynes-Bretthorst algorithm, you can show that when the frequencies are well separated meaning compared to the Fourier frequencies, then you can write the doublet periodogram as the product of 2 Schuster periodograms, exponentiated. This is not an obvious thing. So this is telling you that when frequencies are well separated, the Schuster periodogram tells you everything you need to know about both frequencies. So it might not be obvious, but it's certainly a comfort. So it says that you don't go wrong if the frequencies are well separated, like 26 days and 11 years. You don't go wrong just by looking at the periodogram and looking for multiple peaks. But what happens if the 2 frequencies are close to each other? Then there's no simplification. You actually have to calculate this 2-dimensional function. But what's kind of cool is when you do the math, and I have a little paper on this in the audio engineering literature of all places, but you actually, remember to calculate the Schuster periodogram, you do a projection onto cosines and sines. It's the real and the imaginary part of the Fourier transform. You don't have to do any other calculations in order to calculate this two-dimensional function, but you have to look at the real and imaginary parts separately. That is, you have to worry about the phase information in the Fourier transform. So if there are two frequencies close to each other, you can use the phase information to disentangle them. And this algorithm shows you how. So let me show you two quick examples. So the first one, I have this kind of hobby interest in audio engineering, including like electronics, like measuring the performance of electronic circuits and stuff. And one of the things you do with audio equipment is you measure distortion. How well does the equipment, how linear is the equipment in terms of being able to amplify sound? So the standard, one of the most sensitive ways to do that is this technique called audio intermodulation distortion, IMD. The idea is if you have two frequencies present, if the amplifier is perfectly linear, then the amplified signal has those two frequencies. But if it's nonlinear, then there'll be, like if you Taylor expand its performance, there'll be a squared term. If you take the sum of two sines squared, it has the original two frequencies, but then it also has sums and differences. If you can just add up those, if you use some trig identities, you have two sines times two sines, you have four sines, and then you can combine them in different ways and show that you get the original two frequencies plus differences and sums. So the idea is you put in the two measurement frequencies, and then you look for signals at the sums and differences and use those to measure the distortion. That's intermodulation distortion. So here's an example of how you might do this. So you put in a signal at 7 kilohertz. There's kind of standards that are used for this. So 7 kilohertz is kind of a high frequency in the audible range, but where there's a lot of information, especially about intelligibility of vocal speech and musical signals. 60 hertz is a very low frequency. It's a little lower than the lowest string on a guitar. It's like the middle of a bass guitar's range. And then the difference of these is 6940. It's a frequency that's actually fairly close to 7 kilohertz. So imagine that I have a very good amplifier, but I want to measure its distortion so that the signal at this frequency after I run it through the amplifier is only a few parts in 10 to the 5 of the original signals. So in this case, it's actually below the noise level by a factor of 3. So could I hope to measure this? So currently the way this is done, so standard instruments can't hope to measure this, and it's because of leakage. So here I'm showing a power spectrum, and there's a 60 hertz peak, and there's a 7 kilohertz peak, and then 10 to the minus 5 down from here, there's a little distortion peak, right? But because of leakage, you can't see it. And so there's a company, the leading company for distortion measurement, makes a lot of money selling analyzers that can measure this. And the way they do it is it's like a $5,000 piece of hardware that when you put in the frequencies, it actually adjusts its sampling rate so that this is at one of the Fourier frequencies, so there's no leakage. So as a result, you could find things that aren't too far away from it. But it's very expensive. So to have hardware that will do that. So on the other hand, for $100, you can buy an audio card in your computer that is very linear, but has a fixed sample rate. So I was thinking, could I hope to do this with the standard audio card sampling rate? So what I show here is the doublet periodogram. So this is showing this is one of the frequencies, and this is the other frequency, and there's this, actually this is a splitting, and there's a whopping peak that sticks out, and in fact, without any special sampling, you can easily measure this small distortion product. So I gave this talk at an Audio Engineering Society meeting, and a rep from that manufacturer was there and was very interested, but also not interested in not selling their $5,000, $10,000 hardware. So, all right, here's an ASTRO example. And the way I got into this was with the now defunct SIM mission. So this is work that was done for a NASA mission that would have cost about $1 billion and was built to detect Earth-sized planets around sun-like stars, not looking for the radial velocity signal that I told you about before, but by measuring the star's position on the sky with exquisite precision and seeing stars move side to side on the sky. It requires having a laser interferometer in space. It was going to be very expensive. It was killed, but not before I came up with this idea, but before I published it, so there was no money to publish it. So here's the idea. So the signal, in this case I did write down a radial velocity signal, but it's similar for the side-to-side wobble. You can write down an analytical formula for it. It's a sum of cosines and sines. It has 3 linear parameters, and it has 3 nonlinear parameters. Yeah. This is the period of the planet, the ellipticity of its orbit, how non-circular it is, and then a phase, like when, where time starts in the orbit circle. So there's 3 linear parameters that I can integrate out analytically. So that leaves me with a log posterior that's, what did I say? Oh yeah, period t and these 2 nonlinear parameters. So I integrate out those 3 linear parameters, I integrate out these other 2 numerically, and I can get a function just of period that's custom tailored to the signal that comes from a Keplerian orbit. And so we call that the Kepler periodogram. And I can also do it for 2 planets. So let me show you here what was motivating this for SIM. SIM was going to be a mission that was going to observe for 10 years. And what we were hoping to do was to find maybe solar systems like ours. And most of the exoplanet signal from the solar system, of course, would come from the 2 biggest planets, Jupiter and Saturn. But Jupiter and Saturn, their periods are actually larger than the span of the data. So as a result, they're not resolved. If you do a 10-year observation, you're having less than a full cycle of each. If you were to look at this as a power spectrum estimation problem, all the power from both of them is in one bin at the low end. So it's a terrible leakage problem where, since the 2 frequencies are in adjacent bins, basically, or really in one bin, you can't hope to disentangle them. And so this shows the periodogram, just assuming there's one, actually, I can't remember. Yeah, this was just a periodogram on the signal from a Jupiter and a Saturn. But if you do this, actually this is just a sinusoid, a doublet periodogram, you actually can separate them very easily. And again, it uses the same ingredients used to calculate the periodogram. You do the projection onto the sines and cosines, but you take those pieces and you manipulate them non-linearly in a more complicated way than just adding the squares of them. You actually have to multiply them and combine them in add up different products of them. And it gives you this 2-dimensional function that can actually pull out Jupiter and Saturn from observations that are less than a period of the actual periods of either of them. All right. I think I might stop here.
Well, there is interest in Gaussian processes in this room.
Oh, let me just say let me draw one equation on the blackboard. So I will do that, and then we'll skip the Poisson thing at the end.
Right. There's a little less interest in Poisson in the room.
Okay, so all right, so Peter Whittle is a famous statistician still alive at Cambridge, I believe. I don't know how active he is now, but Did a lot of work on time series and some other things in statistics, but one of the things he's best known for is what's called the Whittle likelihood. And I can't, I didn't have time to refresh my memory on this, but so there are several assumptions. So assume that you model the data with a Gaussian process. So as a result, there's some kind of autocorrelation function of delta t that depends on some parameters theta. Like you might have an ARMA model. So this would be the ARMA coefficients. You might have a radial basis function model. So this would be the amplitude and the length scale of a Gaussian process in the radial basis functions, right? So this is the lag, so the time separation. So this is the autocorrelation function. Then there's a power spectrum, P of omega. That's the Fourier transform of the autocorrelation function. And that's something that's going to depend also on the parameters. Right? So if I have my parametrized Gaussian process model, by definition, this is what you tend to have. From its Fourier transform, I can calculate it for any choice of the parameters, what its power spectrum is going to be. There are some conditions actually, I think the conditions are easiest to write in terms of P. Something about randomness of the phases in the Fourier transform. So, in other words, you want the square of the Fourier transform to have all the information that characterizes the process. You don't want the phase information to be important. And then the final condition is large N. Then what he showed is that the probability for the data, if you know theta, for a Gaussian process, that's going to depend on the determinant of the covariance matrix, and then e to the covariance matrix projected on the data. It's a messy thing, but what he showed is that there's actually a simple approximation to it, and here's what it is. It's actually not so hard to understand, given some things that we've already talked about, and I'll say in a minute what it is. 1 over, let me call this, I shouldn't have used P here. We've used P for the Schuster periodogram. Let's use S here for power spectrum. Okay, so that's something that you have a model for. It's just this is a continuous function of omega that you have a model for. So S at omega j, and the omega j's are the Fourier frequencies. Again, this is equal spaced sampling, equal spaced data. 1 over S, always flip which direction it is, X minus the Schuster periodogram at J divided by your model, which depends on the parameters. So yet another formula relating some probability to the periodogram. So remember, when we viewed the periodogram as a spectrum estimator, it appeared in the p-value in the Rayleigh distribution. So it's something a little like this, actually. When we viewed the periodogram as telling us about the locations of delta functions in frequency space, it was e to the plus periodogram over noise. And then now, when we think there's a Gaussian process behind the signal, we get a product of things that are like the null. This is actually very much like the null distribution that Schuster wrote down for the maximum of the periodogram. But now we're multiplying it for every Fourier frequency. This is basically a chi-squared 2. If I think of this as a distribution for a p, an exponential with some variance. So 3 different ways to use the periodogram to tell you something about the signal. In this case, this is a model that's appropriate if you think, so these conditions, the conditions that you're writing down a Gaussian process model and that the power spectrum tells you everything, this is basically saying that that you're thinking of a stochastic variability, not a delta function, not a periodic thing. And so 3 very different ways to use the periodogram. And so there's only a few people who have used this in astronomy. Jeff Scargill and I advocated for using it, but 2 proposals couldn't get funded, so we didn't. But is it Simon Vaughan? Were you remembering his first name? Simon Vaughan has written a paper on this. Robin Morris learned about it from me and has done some work on this. But it's actually not explored very much. I don't know anything about generalizations of the Whittle likelihood to non-uniform sampling. That would be interesting to know about. It might provide an approximate way to do the kind of ARFMA stuff you're talking about, if there is stuff on that. But anyway, just another thing to know about the periodogram. So,
is there a relationship for a Gaussian process between the variance of the data and the sort of noise in the periodogram?
The variance of the data, and I'm not sure what.
I don't think there's anything simple. I was
just going to get back to there. Between the variance of, so let's see. So if I'm remembering right, the thing that Simon Vaughan did for this was to try to find periodic signals in red noise. So his model was to write the, get rid of just this top line here. He imagined that you have data at some time I, which is some sinusoid. Depends on frequency and whatever other parameters, plus some stochastic function that depends on some other parameters. And then I don't remember if he had measurement error or not. An independent measurement error, I can't remember. It wouldn't be hard to add to this. So then he ended up using the Whittle likelihood for the residuals after you do the periodic fit. So I don't know if that's getting at what you're saying. It's modeling the noise as a stochastic process and trying to actually tune that to match the data. And in his case, for red noise. So it was a non-trivial thing. So in general, I mean, to the extent that the periodogram is a spectrum estimator, so that is to the extent you could figure out good ways to do smoothing and tapering, then yeah, in that sense, it probes the noise, the variability of the data. I don't know if you mean anything other than that.
Well, if you keep an infinite number of coefficients in a Fourier transform, you have the same information. If you have a lot of noise over here, there's got to be a lot of noise over there.
Mm-hmm.
So in that certain sense, it must be noisier for noisy data.
Mm-hmm.
But I guess I just don't know the relationship mathematically.
So from the Bretthorst viewpoint, the James Bretthorst viewpoint, maybe this is actually a bullet I took off because I actually took it off just before I came here because I didn't think I'd be able to explain it simply. But it turns out that if you don't know the noise in your data, so this is somewhat counterintuitive, the amplitude of the periodogram peak actually tells you about the amplitude of the noise, not the amplitude of the signal. It's a subtle thing that comes out of the math. But if you don't know the sigma, then the amplitude of the Schuster periodogram is actually what helps you set the scale for sigma.
Chris Cohen, K-O-E-N, wrote a
Yeah, Chris.
1990s paper, a very short one, on how the exponential function with a peak, which is ideally there, is completely wrong if you don't know the noise level, which is the denominator of the exponential thing. And he showed, that paper, in my opinion, has been undervalued because it essentially means that in practice, no astronomer
like
can
everything Chris does
can ever be used, because you can never get a probability of a peak, because you never know that sigma population variance is never known, because the stars of the galaxies are far away, and you just don't know anything about them. All you have is data. And so this criticism I always felt by Chris Cohen was profound and ubiquitous, and yet the paper's sort of ignored. And I wonder if it's related to what you just said about Larry Bretthorst, who I knew him slightly also. It was very brilliant and insightful. And maybe it's the same.
So he was dealing with a case where the noise is white, but you just don't know the level.
That's right. That's what Cohen said.
Okay, so then that's something you can handle.
You can or cannot?
Yeah, you can.
No, but you can't evaluate probabilities.
No, you can.
Oh, I'm sorry.
If you're willing to make those assumptions.
I see.
If it's white and ID, if it's identical but white and you just don't know the level, then things that were Gaussian in the, it's no longer a Raleigh distribution for the tail area. It's something that gets broadened because instead of that exponential for the periodogram, instead of e to the periodogram over the noise level, it's a student t distribution with the periodogram divided by an estimator of the noise.
Oh, wow. So it is knowable.
Yeah.
There is a probability you can get.
Yeah, there's a Bayesian probability. I don't know.
Is that in his essay in that conference proceedings?
It probably is. Yeah, yeah.
Wow. It's buried there too. There's another interesting result that's buried. Wow. We have to unbury some of these insights about periodograms. There's a lot of naive, just the literature and coming out in astronomy all the time it's very naive and doesn't have the sophistication of Tom's presentation and things that people like Bretthorst and Cohen have written about, and maybe Vaughn. I don't know quite what to do about. It's sort of an advanced teaching problem. Things that are known but not understood, or known to the wrong people, not to the people who need to know.
So I just brought this up as the closing. I wanted to underline again raw. So now I hope you at least know not to, that there are things you can do to the raw periodogram to make sense of it. But there's not one thing you can do. What to do with it depends on the question you're asking. And there's different options that you have to fit to your problem.
Well,
all right.
Thank you, Tom. Not only was it interesting, it was right on time. Are there any final comments by anybody in the room? Okay.
All right, thanks.
Great.